Dear students, we have discussed the growth of charge in a LCR circuit in the previous class. Now we are going to look at the decay of charge in a LCR circuit. So the circuit is similar without the battery, of course. So you have an inductor, a capacitor and a resistor, and they are all connected to a battery for charging initially. Once the capacitor is fully charged or inductor has reached the maximum current, okay, you disconnect the battery and you just short the circuit. So you are left with inductor, capacitor, resistor connected in series in a closed loop, and the charge starts decreasing or the current starts decreasing due to the presence of resistor there. So the rate of decrease is controlled by the resistor and the components in the circuit like inductor and capacitor. Let us see at what rate it reduces. Okay, I will be sending you the photographs of the book anyway, so let us begin. We consider as before EMF of the cell was E. We will not worry about it now because we won't be using the battery now. So we have only these three components. So consider the circuit. You can write it those bits as before, and then you have components L, C and R, and we have to apply Kirchhoff's voltage law. Kirchhoff's voltage law gives you minus L into di by dt, the source on one side, is equal to IR plus Q by C, or rearranging the terms, L into di by dt plus IR plus Q by C is equal to 0. As before, we have to write I in terms of Q. So this is L into d square Q by dt square, since I is equal to dQ by dt. IR dQ by dt into R plus Q by C is equal to 0. Divide by L. So d square Q by dt square plus R by L into dQ by dt plus 1 by LC into Q is equal to 0. So we have brought this into a standard form of the standard differential equation. We have to solve this now. It has got some standard solution. Before that, we have to do a couple of substitutions. First one, we call R by L as 2B and let, and 1 by LC is equal to K square. You will know why we choose those terms like that. Why it is 2B, why not B, you will know later. I think you have already understood it from the charging of the LCR circuit. Okay, so K square 1 by LC has got the dimensions of square of the frequency, angular frequency. So that is why we choose it like that. So now d square Q by dt square plus 2b dQ by dt plus 1 by LC is K square Q is equal to 0. So here the solution is if Q is equal to A e to the power alpha t, if q is equal to a e to the power alpha t, then dq by dt is equal to alpha a e to the power alpha t, and d square q by dt square is equal to alpha square a square, alpha square a e to the power alpha t. So substituting in this equation, I call that equation 1. So substituting in 1, what we obtain is alpha square plus 2 beta b alpha plus k square into a e to the power alpha t is equal to 0, or it is again as before, alpha square plus 2b alpha plus k square is equal to 0. A cannot be 0 because we have defined a as a amplitude, and e to the power alpha t also cannot be 0. It is 0 only at t is equal to 0, otherwise it is not 0, because if it is 0, why we take a e to the power alpha t as q. So q is not, charge is not 0. It is 0 only at the end of the experiment when everything is discharged, but until then it is not 0. Since a e to the power alpha t is equal to q is not equal to 0. So that means the other term has to be 0, and this is a quadratic equation in alpha. So that gives alpha is equal to minus b plus or minus square root of b square minus k square are the two roots of the equation. Therefore, the general solution for q is equal to a1 e to the power minus b minus plus square root of b square minus k square, everything into t, plus a2 into e to the power minus b minus square root of b square minus k square into t. Okay, and I call this equation 2, and I will do, we need also the current, so I is equal to dq by dt is equal to, just differentiating that puts these terms next to a1, so minus b plus square root of b square minus k square e to the power alpha t, alpha e to the power alpha t on differentiating, into a1 is anyway there, e to the power minus b plus square root of b square minus k square into t, plus minus b minus square root of b square minus k square into a2 e to the power minus b minus b square minus k square root of into t. So that is the equation, I call that as 4. Now we apply the boundary conditions. There are two boundary conditions. One is, first one is at t is equal to 0, q is equal to q naught, and I is equal to 0. So these are the two conditions. So from that, equation 2 implies a1 plus a2 is equal to q naught. It is nothing but the sum of the constants a1 and a2 is nothing but the total charge that was there at the beginning of the experiment when time was 0. And second one gives you minus b plus square root of b square minus k square into a1 plus minus b minus square root of b square minus k square into a2 0, because I is 0. So I is equal to 0 takes you to this equation. From these two equations, they are like two equations and two unknowns, from which you have to calculate the two unknowns. It is something like you used to have in school. 5x plus 6y is equal to 8 and 3x plus 9y is equal to 11. Calculate x and y. So it is something of that type. So from this equation you can calculate a2. You can rewrite this for a2. a2 is equal to a1 into minus b plus square root of b square minus k square divided by b plus b square minus k square. We are just rewriting it, nothing much. So and if you substituting in, let us say 4, you get q naught is equal to a1 plus a2 is equal to, so in the place of a2 I will write the new term, a1 into minus b plus square root of b square minus k square divided by b plus square root of b square minus k square. Alright. So therefore a1 is equal to q naught by 2. You can do the rearranging steps, not very difficult. So I just put 3 dots. So 1 plus b by square root of b square minus k square, and a2 you get q naught by 2 into 1 minus b by square root of b square minus k square. If you can't solve this step, just let me know. I can give you the intermediate steps. Okay, you try it and then let me know in case. Okay, so from these we write, therefore the general solution will be, you just write for a1 and a2 in the previous equation. So it's a bit lengthy equation. Q is equal to q naught by 2 into 1 plus b by square root of b square minus k square bracket close e to the power minus b plus square root of b square minus k square, entire term in the bracket, into t plus q naught by 2 into 1 minus b by square root of b square minus k square, bracket close, e to the power bracket minus b minus square root of b square minus k square into t. So let us call this equation 5. So that is the general solution for this equation. So which this equation explains how the charge is changing in the circuit. Okay. Next we discuss different cases here. Different cases by comparing b and k, because that is the term. So comparing b and k, 3 cases. First one is b square is greater than k square, or b square minus k square is greater than 1, b square is equal to k square, or b square minus k square is equal to 0, and the last case is b square is less than k square, or b square minus k square is less than 1. So these are the three cases that need to be studied separately. Of these, first two cases are very clear. So case 1, b square greater than k square, so charge decays exponentially. Charge decays exponentially because there are no complex terms. So it's known as over damped or deadbeat. Case 2, again not a serious issue. So then you get q is equal to q naught into 1 plus bt to the power e to the power minus bt. So it's a non-oscillatory discharge or also known as critically damped. This is also known as critically damped. In a so this is exponential decay. It is an exponential decay. So what they look like, you can see the graph on page 172. So we just plot q as a function of t. First one is decreasing exponentially, second one decreases a bit faster. So case 1, case 2, this is case 2 is critically damped or quickly it damped. So the meaning for damp means decrease or reducing. And the third case, damped oscillations of a tuning fork, you might have heard. So you hit the tuning fork, it makes a loud noise and slowly the noise decays. Case 3. Case 3, the case when b square is less than k square, or b square minus k square is less than 0, or we can also say minus 1 into k square minus b square is less than 0, or k square minus b square is greater than 0. So and then here we call square root of b square minus k square as j omega, and square root of k square minus b square as omega, which is positive. So this is positive, this is imaginary. Okay, so therefore equation 5 implies q is equal to q naught by 2 into 1 plus b by j omega into e to the power minus b plus j omega into t plus q naught by 2 into 1 minus b by j omega into e to the power minus b minus j omega into t. We take the e to the power minus b out of this, so q is equal to q naught by 2 into e to the power minus bt. That gives you e to the power j omega t plus b e to the power j omega t divided by j omega plus e to the power minus j omega t minus sorry b e to the power minus j omega by j omega. Again you do the rearranging of the terms a little bit, and q naught into e to the power minus bt, I take 2 inside, so e to the power j omega t plus e to the power minus j omega t by 2 plus b by j is common in these two. Okay, so b by j I keep outside, and inside 2 omega b by omega outside, sorry, j has to go inside. It's the complex number that should be inside. E to the power j omega t minus e to the power minus j omega t. Sorry, this is not there actually. Okay, which are nothing but cosine and sine term. So that is nothing but q naught e to the minus bt into cos omega t plus b by omega sine omega t. Okay, what we do is to get the similarity inside, we I just multiply by k by omega, or multiply and divide by k omega. So q naught e to the power minus bt, let us see what happens. So I take k by omega out, that adds to first term omega by k into cos omega t plus, sorry, p by k. All right, let omega by k is equal to cos theta and b by k is equal to sin theta. They actually have the dimensions of angle, that's why we are taking in this way. Okay, so that implies q is equal to q naught into e to the minus bt by omega k. Just a minute, there should have been k, yes, k by omega, so into omega by k is cos theta cos omega t plus sin theta sin omega t. Of course there was k in the numerator outside. Okay, k was there, yes, it's missing in the book, looks like it's missing in the book, so just be careful. And that is you use the sum into products, the formula for trigonometric identities, and that is q naught into e to the minus bt by k in k by omega cos of omega t minus theta. That entire term can be written as a, so a into cos omega t minus theta, where a is equal to q naught e to the power minus bt by omega. So this is the exponential decay term. This one, okay, exponential decay term. This is oscillatory term. So this, therefore, it is damped oscillatory, damped oscillations. So this is damped means decay, oscillations means it's oscillating between two values, and the frequency oscillations is given by f is equal to omega by 2 pi, and that is square root of k square minus b square by 2 pi, or it is given by 1 by 2 pi square root of 1 by LC minus r square by 4L square. That is the equation. So if r is equal to 0, then you have f is equal to 1 by 2 pi square root of 1 by LC. And if you plot this now here as a function of time, it will be a decay followed by an oscillatory, something like that. So I will just draw the previous course also. So case 1, case 2 and case 3. Damped oscillatory, critically damped, over damped. So somewhere here you have Q naught, the maximum charge, and that is 0. So with that we complete this chapter. Questions will be asked from the portion until this class. For the exam that will be conducted this weekend, most probably I will send the questions on Saturday or Sunday, and you have to return them by Monday. You have 1 day's time to answer the questions. See you then.